Hi everyone, this is Team AB and we'll be presenting on the GE F414 engine.
For precursors to the F414, we see the first supersonic engine, the XLR-11, nicknamed the Black Betsy. This is followed up by GE's first supersonic engine, the GE F101. GE would later go on to develop the GE F110 and F118, which is a modified version of the F110 to fit mission requirements. The F414 was developed by GE at the request of the US Navy and saw significant thrust improvements at all altitudes, as well as 3 to 4% reduced specific fuel consumption at cruise. The design effort began in 1991 with test flights beginning in 1995, which is an incredibly fast development cycle. This was helped by highly integrated implemented product teams, which reduced test cycle time by 20 to 60% among all teams, cut down design changes by 2/3, and required only a quarter of the budget compared to previous GE engine development.
A testament to how successful the F414 was how well implemented it was both domestically and across the globe. The US Navy was the largest stakeholder for the engine, producing over 600 fighter jets with it. NASA also announced a new experimental plane, the NASA X-59 Quest, which will also be using the reliable F414. Other countries that partnered with GE include Sweden and South Korea, with Sweden producing over 150 Saab Gripens, and Korea soon to produce over 120 KF-21s. These international deals are not only important for the success of the F414, but also for the strengthening of foreign relations of the United States.
The design requirements the GE F414 was held to were similar to the design requirements of other engines used on multi-role fighters. And we made a couple of assumptions in our requirement calculations, those being that the efficiency parameters given in the textbook Hill and Peterson are accurate for this engine application, that the engine specifications not released by GE were reasonably approximated, that calculations done for the Super Hornet were done at sea level, and that bleed effect and variable nozzle area effects are negligible.
The image on the right shows the different thrust and other engine performance parameters for the F404, the F414, and the F414 EPE variant. As you can see, there has been a notable thrust increase in the F414 from 84 kilonewtons to 98 kilonewtons. The airflow has also been improved from the F404, which was originally 70 kilograms per second to 77.1 kilograms per second, with a further improvement to 85 kilograms per second for the EPE variant. This trend can also be seen in the specific thrust. Part of our analysis was calculating the engine performance parameters throughout the engine. That means the pressure and temperature in the diffuser, fan, compressor, burner, both stages of the turbine, as well as the exit. Some interesting results that resulted from this were we got a dry specific thrust of 815.6031 newtons per second kilogram. This would be an improvement from the F404 due to the largely increased thrust, despite also having an increased mass flow rate. Due to the larger increase in thrust, the F414 also has a higher burner exit temperature at 1922 Kelvin. This is a result of the crystal alloys used in the turbines, which can withstand higher temperatures, as well as overall turbine design improvements. The EPE variant should have further increases due to further improvements in the turbine design. Finally, the thrust-specific fuel consumption calculated was 3.6373 times 10 to the negative 5. This should be lower than the thrust-specific fuel consumption of the F404, since its thrust, once again, is much higher than the thrust of the F404. Although the fuel mass flow rate is likely slightly higher as well for the F414 due to the increased flow rate overall throughout the engine. In general, it's shown to be a massive improvement from the F404 to the F414.
And going off of these results as well, the GE F414 has a lower specific fuel consumption than its predecessor, the F404, which indicates that it has a higher fuel efficiency for longer range and it has a higher thrust to weight ratio than the F404. As well as we mentioned prior, the higher mass flow than the F404.
In conclusion, although a product of the 90s and already decades old, the F414 continues to outperform more modern engines. Its adaptability allowed it to be implemented into many different platforms and use cases. With its great reliability, we can expect F414 to be continued to be used in new aircraft with both research and development. The following are the image sources used for this presentation. Thank you.